Hello guys, this is Paul McWhorter with TopTechBoy.com, and we're here today with episode number 50 in our incredible new tutorial series where you're unleashing the power of your Raspberry Pi Pico W. What I will need you to do is pour yourself a nice tall glass of ice cold coffee. That would be straight up black coffee, poured over ice. No sugar, no sweeteners, none needed. And as you're pouring your coffee, as always, I want to give a shout out to our friends over at Sunfounder. Sunfounder is actually sponsoring this most excellent series of video lessons. And in this class, we will be using the Kepler kit for Raspberry Pi Pico W. Now, most of you guys probably already have your gear, but if you don't, look down in the description. There is a link over to Amazon. You can hop on over there and pick your kit up. And believe me, your life and my life are going to be a whole lot easier if we are working on identical hardware. But enough of this shameless self-promotion. Let's jump in and talk about what I am going to teach you today. And what I'm going to do is I'm going to give you the homework solution for the problem that I gave you in lesson number 49. And what was that problem? That problem was that we've gone through kind of like 4 lessons trying to get better and better and better performance from our tilt meter that we can measure. We can measure pitch and we can measure roll, but we want to continue to refine the results so that we get the most elegant solution possible. And what I showed you last week is I showed you that you can create a complementary filter, and the complementary filter will sort of combine the best of both worlds of the accelerometer and the gyro data. It'll remove the low, remove the high frequency noise from the accelerometer, and it will remove that long-term drift or that long-term low frequency error from the gyro, and it'll combine those two things, and it will create a result that is fast and accurate and low noise. Okay, and we were successful with that. But what we found when we got that stupendous result, we found that if we zoomed in, we know that if it's sitting still, the right answer is the accelerometer data, the result from the accelerometer. And we saw that after going through the filter, there was this little tiny error between the exact answer on the accelerometer and the improved filtered answer coming from the complementary filter. And so what your homework assignment was to drive that long-term steady state little tiny error to 0. Were any of you successful? If you were, leave a comment down below. I am legend. Double chest bump. And if you weren't, I folded up like a cheap Walmart lawn chair. Okay. Now, these are things that you're taught in college, a lot of times like at a master's of science and electrical engineering, kind of at a master's level, you start getting into this stuff. But what I want to show you is it's really pretty simple. I'm going to explain it to you in a way that you'll see it and understand it. And then you'll have a new tool in your toolkit when you run into this same problem on other sensors and other projects. How do you drive that last little bit of steady state error to 0? If you are doing a PID motor controller, you're going to run into this. If you are doing something where you're trying to do a control system to control the temperature accurately in a hot water heater, just almost any type of control system or anything dealing with sensors, lots of times you run into this problem. I want to kind of show you a solution to it. Okay, I'm going to show you a solution to it. Okay, but in order to do that, I will need to get out of your way. And then I don't want to start from scratch. So let's start where we ended up last week, where we had created the pitch and roll measurement that had the complementary filter on it. So I need you to go to the most excellent www.toptechboy.com. I need you to use this this happy little search icon here, and I need you to search on something like improving accuracy of the MPU 6050 data. This is the schematic of how we have our circuit hooked up, and then this is that dandy program that we developed last week. So I'm going to get that dandy program. Now we are going to come over here to Thani, and I'm going to paste it in. Okay, that looks good. And now we're going to run it just to kind of get reoriented to how well this works, how elegantly it works, but then the one minor little problem that remains. And so I'm going to run it, and there it goes, and it should auto scale here, and then it should calm down a little bit. What I really want to compare is I want to compare, let's see, I think it is the pitch of the accelerometer, which is orange, and the pitch of the compensated in red. And so you see between the orange and red there is a tiny bit of error, and that error isn't going away. But now if we actually look at pitch, you know, we're really doing a good job in pitch. You see they're tracking, and particularly if we look at that, particularly on pitch, if we look at the red one, okay, when I shake it, you see there is no noise on the red. The red is rock solid. The orange is the accelerometer, and it's got the noise. Okay, so with the red, we have filtered out that noise, and when we look at the red, there's no long-term drift. There's no short-term noise. There's no long-term drift. But what do we have? We have this tiny steady-state error that doesn't seem to be going away. Now we could play with our parameters and we could kind of get it to go away. Like we can see that to get that to go away, we probably need to give a little bit more weight to our anchor, the accelerometer. And so like if we put this at 0.1, we put this at 0.1, and then we went 0.99 on the other ones. Now we're probably going to get rid of that long-term steady state drift, or we're going to really eliminate it quite a bit or reduce it quite a bit. So now we can see that the difference between the orange and the red is a lot less. Okay, it's a lot less now by playing with those parameters. Okay, you see we've almost got it to go away, but now what you can see is in doing that, I've incorporated now a little bit of error. I've incorporated a little bit of error in that red, in the compensation. So what I want to do is I want to go back to 0.005 and 0.005, and then I want to go 0.995, and I want to go 0.995, and I just want to tell you, and you can try it if you don't believe me, but you can never really drive out that steady state error. You can never really drive out that steady state error just by playing with these parameters. Now you can see it doesn't look like on the roll, it doesn't look like you have one, right? It really doesn't look like that you have an error on the roll. But let's see if we can look into that a little bit further. And if I come here, and this time, let me get this, I'm going to copy it, and then I'm going to paste it, and then I'm going to comment it out. And this time I want to look only at roll. So I'll look at roll on accelerometer. I'll get rid of this. And then I'm going to look at the roll compensated. I'm going to get rid of this. So we're only looking at the two roll values now. I'm going to go like this. Okay, and what do you see? Even in roll, there's about a half a degree of error. Okay. Do you see that that orange is not being perfectly on the blue, even though there it looks like it's because it's auto scaled. Let's look at it again. Even here you see there is a long-term steady state error that is not going away between the compensated data and the actual data from the accelerometer. Okay, so sometimes it's bigger, sometimes it's smaller, but we want to get rid of it. Okay, we want to get rid of it. So let's go ahead and put our old print statement back in there. Take that out. Let's look at it again, just get a clean run. Okay, you see we've got a long-term steady state error between the red and the orange. The red is the filtered, beautiful, fast, accurate, low noise, no drift value, and the orange is the actual exact value, and there is an error between those, and we want to drive that error out. Okay, how are we going to do it? Well, let me kill it, and let's just say that you can't do it by playing with these parameters. These parameters are affecting our filtering of the high frequency data, and they're affecting the filtering of the long-term drift, that low frequency drift and the high frequency noise. It's dealing with those two, but it's not dealing with a constant steady state error. And so what we've got to do is we've got to see that I have got to incorporate this concept of error. Okay, to deal with it, I've got to introduce this idea of error. And I have to distinguish between an error that might be a noise error, an error that is just a long-term drift. We've dealt with those, but I've got to deal with the steady state error. Now, how do I know if it's a steady state error? If it's a steady state error, it stays. And so how do I know that I have an error that stays? I'm going to just keep every time adding the error up. Every time through the loop, I'm going to add the error. And if that error is building up, then I'm going to squeeze it down. I'm not dealing with the error like this. I'm not dealing with the drift error. I'm dealing with the error that is constant. So how would I do that? Well, I'm going to introduce this concept of, let's take the error in the pitch, the error P, because that's the big one, that's the one that's the problem. And then what I'm going to say is, I'm going to say that that error in pitch is going to be the pitch accelerometer, which is the actual pitch, okay, minus the pitch compensated, which is the one where we've taken the high frequency vibration out and we've taken the long-term drift out. Now I'm left with what? Error P. Well, what's the problem? If I just look in the middle and I get that error, how do I know that that error isn't vibration? How do I know that error isn't long-term drift? Well, what I want to do is I want to add it up. So I'm going to take the error and I am going to multiply it by how long have I had that error. I've had it for the amount of time since the last time through the loop, so T loop. Okay, so if I have that little error and I loop and I loop and I loop and it's still there, what I'm going to do is I'm going to add it to the error P. All right. Now, what is going to happen here? What is going to happen here with this error? If it's a noisy error, then error P is just going to not matter. It's going to be close to zero because it's big this time, it's little this time. It's going to average out to zero. But if it's sitting there constant, it is that error times the delta T plus the error times the delta T plus the error times the delta T. It's growing. And initially it's little and you don't know, but as it gets big, you've got to deal with it. Okay, so this error, it's the integrated error, the sum of all the errors, they're building up. And what have I got to do? I've got to squeeze them down. Well, let's go ahead and let's do the same thing. Let's do the same thing, but for the error in the roll, and the error in the roll, and this would be roll accelerometer and roll compensated. And so now what I've got is I've got this bag that I'm carrying, and that bag gets heavier and heavier and heavier because every time I'm adding, you've got error, you've got error, you've got error. Okay, now I've got to squeeze that error out, and I'm going to come up here, and whatever that error is in roll, okay, I'm going to compensate that. I'm going to compensate for that by adding an error correction term. And I will say that is error times P. Error P, that's my error in my pitch. And then times, let's just say 0.01, like that. Okay, so I don't want to squeeze that error out, that constant error. I don't want to squeeze it out all at once, but I want to kind of drive it out. I want to squeeze it out. If I say 0.01, 100 times through the loop, it will squeeze it out. But that way I don't start impacting the high frequency stuff and the other stuff that I've just done. After all of that is done, now I've got this squeeze function that is going to squeeze out this integrated error, right? I've got this integrated error that I'm carrying on my back that's getting heavier and heavier. Now I'm starting to throw it away, and I'm going to keep throwing it away until what? Until it is not there anymore. So it's going to be that, and then same thing here. It is going to be plus error, that was error pitch. Okay, I did that wrong. That would be error roll, and this would be error pitch times 0.01. Now notice this and this have to equal 1 because that is fusing the data between the accelerometer and the gyro to have something that is fast, something that is accurate, something that doesn't have drift, and something that doesn't have noise. But after doing all of that, I end up with this annoying little error. Now I'm going to come out here and I'm going to squeeze it out by taking 1% of the error, 1% of the error, and then driving that out each time through. So remember before, the pitch had a long-term steady state error of what? It was about 3 or 4 degrees, it looked like. And so now let's see what happens. And we want to keep our eyes on pitch, okay, because the pitch was the orange and the red. Okay, so that orange, that compensated, should be pushed up now towards the red. So let's take a look at it. Error R isn't defined. Oh, yeah. What have we got to do, right? This was one of those error R's plus error R's, right? So we have like the error P was the old error P, the error R was the old error R. We've got to set those. We've got to set these up here at the very top. So we're going to say error R equals 0, and we're going to say error P equals 0, and that way it won't crash the first time through. So now let's run it again. Okay, look at the orange and the red. You see how they are apart, but what's happening? The red is chasing the orange. Do you see the red is chasing the orange? And now what's happened? We've driven that error out between the orange and the red. How? The red chased the orange, and it says, I don't like this burden I'm carrying of this sack of errors. I'm going to start throwing it away. And so let's watch it again. Let's watch the red and let's watch the orange. Okay, look, orange and red are what, like 3 degrees apart? The red chased the orange, it passed it, it's coming back, it passed it, and now it is stabilized. Boom, just like that. What do you also see about the green and the blue? The green chased the blue, and the green put itself in the middle of the blue. Okay, you see green and blue? Watch that. The green is chasing the blue, overshot it, it came back, overshot it, came back. Boom! The green caught the blue, and the red caught the orange. Now let's see if this thing still works. So I'm going to come up, and let's just say I'm going to pitch it. Okay, I pitch, and look at this. Right, the compensation is still working. You're looking at the red, that's the compensated, and look at that. No noise in the red, right? No noise in the red. I guess I should show you how I'm tilting this thing. So I'm going to pitch, and look, boom, red and orange are exactly the same, but now when I introduce a vibration, red is rock solid, Why? Because red's not chasing that error. It's only chasing the error over time. It's only chasing that steady state error. Now, I think if I drop this, I will introduce an error because I'll move it faster than it can make the measurement. And so when I do that, I think that you'll see an error between red and orange, but then I think you'll see red chase orange again. So I'm going to bring it up, and then boom, look, red is chasing the orange. It passed it. It's going to come back, and then it kind of zeroes in on it. Boom! Red caught orange. Red caught orange. Okay, now you could imagine that you could affect these things. So you see, watch now, red. Now when I come down, it takes a while for red to catch orange, right? It takes a little while for red to catch orange to drive that out. So what could we imagine doing? We could imagine coming down, and instead of dropping 1% of my error, 1% of my accumulated error every time, what if I dropped 10% of my accumulated error every time? Do you think that's going to, orange is going to catch red, or red's going to catch orange faster or slower? Okay, now you're probably going to think faster, but watch red chase orange. Okay, it's going to have to rescale. Okay, red is chasing orange, but what's it doing? It's going so fast, it's overcompensating. Let me try it again. Watch red and orange. Red is going to chase orange, and look, red goes over, then it goes below, now it's above, now it's below. And so we tried to make it go faster, but it's what? It's unstable. It's unstable. All right, well, let's try something else. So instead of 0.1, let's say 0.001 and 0.001. Now it's going to be what? It's going to be very, very stable. Red's going to chase orange. Okay, look, red is going to chase orange. Red is chasing orange. Red is catching orange. Red is catching orange. Red is catching orange. It's very stable, and it comes up. Red is chasing orange, and then it just comes in perfectly right into the middle. It didn't go above and below and above and below. It just came perfectly up. But what did we not like about that? It was slow. So we want it to go faster. So 0.001 is very smooth, but it's too slow. And 0.1 is very fast, but it overshoots and oscillates. And so what seemed to be kind of like the magic one, it was about 0.01, like that. Okay, let's run that. Okay, red's chasing orange, and it comes up, it overshoots a little bit, and then it undershoots a little bit, and then it's just perfectly on there. It is perfectly on there. Maybe I would slow that down a little bit. What if we said 0.05, 0.005 and 0.005? And maybe it would not quite overshoot. Okay, red is going to chase orange. Red is chasing orange, and it comes up. It overshoots one time, and then there it has it. And so maybe 0.05 is a pretty good value for having that. So now let's see what our overall performance is of our sensor. I am going to roll, and boom, it comes up, and the error is driven out. Okay, I come down. It comes up, and that long-term error is driven out. I roll, it's tracking it perfectly. I roll, it's tracking it perfectly. When I shake, you see green stays steady. It ignores the shaking of blue. Okay, green stays steady. And now I'm going to pitch, and then you see orange is a mess, but red stays steady. And then if I drop it, it gets a little bit of error. But what? The red chases the error out and goes to orange. Does this make sense? Do you understand the difference between the three types of errors that we have and how we deal with them differently? With short-term noise, we apply a what? A low-pass filter. With the long-term drift, we apply a what? We apply a high-pass filter. Okay, when we have some element of both of them, we do a complementary filter where we take the best of the accelerometer data and combine it with the best of the gyro characteristics, and then we get something really good. But then we get annoyed that when we do all of that, we end up with some long-term steady state error. And so what do? We drive that error to zero by adding in this correction factor, and then we get everything working perfectly. Man, do you guys hate me now? It's like, how many of these lessons did we do? How many of these gyro lessons did we do? I'll see if I can tell you. We went back to the and it was like lesson number 38. That couldn't be right. We couldn't have done 12 lessons. We couldn't have really done 12 lessons on the MPU 6050. I'm sorry. I'm sorry that I got sidetracked with this, but what I want you guys to see is it's not about the MPU 6050. It's not about tilt, and it's not about roll. What it's about is we live in the real world. And when we live in the real world, we get real world data. And that real world data often has noise in it. And that real world data often has drift in it. And that real world data often has steady state errors. And I'm showing you the techniques to drive those three different types of errors out and get something that is really cool and clean data. Like some of you guys have been talking about maybe something that would open and close your garage door or warn you if the garage door was open, and you wouldn't want that MPU 6050 to vibrate and then your door just start going up and down, right? You got to clean the data up. And so I'm showing you that in real world applications, you've got to be able to do that. Okay, I lied. There's going to be one more lesson on the MPU 6050. And what I want you to do now is I want you to come in and I want you to use this improved best version of roll and pitch, and I want you to go back and make your little tilt meter now, where you've got the reticle and the crosshairs and the little bubble moves in response to the pitch and the roll. And so now bring it all home by putting that on here and having a deluxo, probably over-engineered, and no one has ever built a level this accurate in the history of the universe. But put it all together and get the display going, and then we will call it a wrap on this. Okay, guys, I really hope you don't hate me. I really hope you don't hate me, but it's just I want you to learn these things. And if I just created a lesson that said, okay, here's how to do a low-pass filter, you're going to wonder why, and then you're not going to remember it because it didn't matter. So I taught you a low-pass filter in the context of a real problem where you had noise data and needed to get rid of it, and I showed you how to get rid of it. I showed you how to do a complementary filter. Why? Because you need to get rid of it. I showed you how to get rid of a long-term steady state error because you need to get rid of it. So you'll now know how to do it, and you'll remember it, and you will know that it is important. I do hope you guys are having as much fun taking these lessons as I am making them. I want to give a shout out to you guys helping me out over at Patreon. You're the ones that are keeping me in the game. YouTube has made it clear that they don't like grumpy old guys making long videos. They like cute young girls with 20 seconds in front of a video short. That's the direction YouTube's going. You guys that are helping me out on Patreon, you're keeping me in the game, and I thank you for that. You all can also help me by giving me a thumbs up. Also helps if you leave a comment down below. If you've not already, subscribe to the channel. When you do, make sure you ring that bell so that you'll be notified when future lessons drop. And as always, share this video with other people, because the world needs more people doing engineering and fewer people sitting around watching silly cat videos. Paul McWhorter with TopTechBoy.com. I will talk to you guys later.